but I haven't transcribed the grades yet. And my impression is that people did significantly better on this one than on the last one. And I'll know when I do the averages and all that. But it looks as if a lot of people are doing the work and are figuring stuff out, and that's good. That's the good news. So a lot of people, I think, are doing exactly what they're supposed to be doing. Those of you who are studying and maybe are a little bit disappointed that it's not paying off quite as much as you hope, don't get discouraged. Okay, so as long as it's coming together, even if it's not quite as coming together quite as fast as you think, you need to be patient. Just keep doing it. Okay. So I mention that because I know a lot of people are putting a lot of time into it and say, well, gosh, I put all this time and I didn't get 100%. Don't think that way. Just think about incremental progress. Okay. And you need to do this not just for this course, but for any other challenge you face. Now that's the good news. The bad news is that we still have a cohort of people who are not doing any work. And I guess in a class of this size where I get 40% people not showing up on any particular day, moving around today, it shouldn't surprise anybody if roughly 40% don't pass, right? I mean, that's just the way it goes. But that's a bit disappointing. It seems like there's kind of two kinds of students here, ones who are taking it seriously and ones who are not. And I can't change that. Okay, so let me go over just a couple of the common errors that I saw in the exam. And let's try to make sure that we understand, that we can understand what the error is, and then move on. Okay, so this was one that I saw again and again to the point where I really had to suppress and urge to strangle students. Okay, what's wrong with that structure? Yes, octet rule. So since everybody can see this, not everybody can see this. I saw this mistake too many times. Okay, so yeah, let's get rid of that abomination. Now there's another mistake I saw, and hold on. There's another mistake I saw, and I want you to tell me why this is no good. Why is that no good? Okay, so you guys can see it. Oxygen has too many bonds. Is it an octet rule violation? Oh, very good. No, it's not. The reason this is no good is because if I have the structure, this oxygen atom would have a +2 charge. And that means putting 2 positive charges on an electronegative oxygen atom. It ain't going to happen. Okay? So I saw this not quite as often as that. Now, the one mistake, the other thing I want to say was that the class in general kind of choked on the synthesis problems. And the synthesis problems, from my point of view, were much easier than the mechanisms, where people actually did a lot better. And it goes to show why synthesis problems have a really nasty way of highlighting what you do and don't understand. So I saw all kinds of really not good things on the synthesis problem side. They were 2-step syntheses. Okay, each one of those was 2 steps. Just had to do 2 steps to get from the starting material to the product. It doesn't get any simpler than that. Okay. So I'm not saying this to make you guys feel bad, but you need to work on that one. And so that's something you need to work on a lot. Now, for the mechanism problem, here's something I saw, and you need to not make this mistake. Okay, we spent a lot of time in this course talking about what? About acid-base chemistry. And so this is a mistake I don't want to see you guys make. So I saw a lot of people get started on that bisphenol A problem, like so, okay? And they show this happening. Now, there are a number of reasons why you should never have gone down this pathway. The one reason is that you look at that bisphenol A problem, it's just an electrophilic aromatic substitution problem. If It's electrophilic aromatic substitution. Have we ever had to pull a proton off of a benzene ring? And the answer is no. So don't go looking for stuff that you don't need to do. Now, the next thing has to do with pKa's. So you don't have to memorize pKa's, right? But a lot of what we talk about for acid-base chemistry is qualitative, and that's all you need. So let's take a look here. I have 3 protons that I need to be thinking about. That one, this one, and water. Okay, so I have an acid-base reaction taking place here, supposedly. Of course, I could have this acid-base reaction, and I'm forming an acid and a base. Okay, so of the 3 protons, this one, and that one, which is the most acidic and why? You don't have to tell me what the pKa is. You just have to tell me which one is the most acidic. Let's count. 1, 2, 3. Most acidic. Yeah, it's got to be this one. Why? Well, because the conjugate base is on an oxygen atom, which is electronegative, and it is resonance stabilized. So this is the most acidic proton. The next most acidic proton is this one, because why? Well, because the conjugate base is on an electronegative oxygen atom, and the least acidic proton is that one. So in other words, this will never happen. Now, you need to remember a little bit about pKa's. pKa of this kind of a proton is about 40, something between 40 and 43. pKa of this one is about what? About 10. And pKa of water is what? Around 15, 16, right? Okay, so since you know, or supposed to know that, this is not, you don't want to get started down this pathway. The other thing to remember is, there's another reason why you don't want to do this. There's about 10 reasons why this makes no sense. The other one is, you're doing this in acid medium. What do we say about acid medium? If you have an acid catalyzed reaction, you're not going to find hydroxide in there. There is no hydroxide. The concentration of hydroxide is essentially 0 in acid. So where are you going to find the hydroxide when there's H3O plus around to catalyze this? It's not there. And so this mistake I saw way too often on the exam. So you need to kind of think about, you don't have to memorize pKa's, that doesn't do you any good really. All you need to do is be able to figure out which is the most acidic, least acidic proton, and then remember what we said about acid catalysis versus, concentration of hydroxide. Similarly, if I have a reaction that's catalyzed by potassium hydroxide, don't look to find any H3O plus in there. There isn't any. Okay, so, yeah. Okay, so, anyway, for those of you who just walked in, I'm going to have the exams back here on Wednesday. Let's pick up where we left off on Chapter 20. Chapter 20, recall we talked about decarboxylation reactions. And we said that this is generally not an easy process. Splitting out CO2 from an acid, carboxylic acid, is usually a process that requires high temperature, catalysts, and so on, sometimes conditions that are not really easy to achieve in a research lab. But there are a few exceptions to this rule, and the exceptions are given here. Beta keto acids, or beta carbonyl acids, and also the monoesters of carbonic acid. These undergo essentially spontaneous decarboxylation. I shouldn't say spontaneous. In the case of the first two, you need to heat them up a little bit. But the decarboxylations are rapid and fast reactions. And so evidently the presence of this carbonyl group confers a special kind of reactivity on that carboxy. And so, in other words, if I had the ketone was one carbon further away or 2 carbons further away, it wouldn't matter. I mean, then decarboxylation would be a very difficult process. But when the ketone is right there, then yeah, this becomes an easy decarboxylation. The reason was that mechanism that I showed is the last thing on Wednesday, and that is a mechanism whereby you get a concerted process. You end up transferring the proton from the carboxylic acid group to the carbonyl, and then at the same time moving electrons in such a way as to spit out CO2. And so you can do that whether you have a beta ketone or beta ester. And so these reactions take place very, very easily. Carbonic acid also is, as you know, it's an equilibrium. It's just the equilibrium product of CO2 dissolved in water. And if you have monoamide or monoesters of carbonic acid, so monomethyl carbonate or carbamic acid, these undergo decarboxylation rather easily as well. On the other hand, if you have the diester or you have urea, these compounds are stable. Another one that is unstable and that people try to use on the exam is this stuff here, the monoacid chloride of carbonic acid. This stuff doesn't stick around. This is unstable. It's just HCl and CO2. So this is not something you can get your hands on. Okay, so decarboxylations in general are going to be difficult to do with these few exceptions. And then just to amplify what I said, dimethyl carbonate is stable. So this stuff is actually fairly pleasant smelling stuff. It's liquid, you can buy it, it's cheap. The diacid chloride, unlike the monoacid chloride, the diacid chloride of carbonic acid is phosgene. That's that war gas, okay? And phosgene is a gas, and so as a result, it's not very easy to work with in the lab. You can buy this stuff as a solution in toluene. It's a little bit dangerous to work with. It's much easier to use triphosgene, which is a solid. Now, you look at this, you look at that, and say, what do you mean triphosgene? You know, I mean, I don't see how that's triphosgene. But actually, this stuff decomposes to that in solution. I'm going to leave that kind of as a problem. Kind of figure out how this might convert itself into that without too much, without too much difficulty. So you can use triphosgene, which is a solid, still poisonous, but not volatile, not as volatile as phosgene, easier to work with, safer, and do the same kinds of reactions that you could do with phosgene. The monoacid chloride monoester, which is called ethyl chloroformate, bad name, but that's what it's called. This stuff is also cheap, available, and easy to work with. So bottom line, you don't really have to use phosgene. You have alternatives that give you the same kind of reactivity, more or less, as phosgene. And what that reactivity is going to become evident in the next chapter. Okay? So in the next chapter, we're going to be talking about carboxylic acids, derivatives, i.e. esters, amides, and whatnot, and how they react. But before we do that, I'm going to spend a little bit of time talking about decarboxylations in biology. And it turns out that biological systems are known that catalyze a decarboxylation reaction. Now, this turns out to be a very interesting process. It uses vitamin B1 as a coenzyme. Okay, so remember what a coenzyme is. For biological processes that are catalyzed by enzymes, very often you have a species that's not part of the enzyme, separate molecule that does something to it. It's necessary for the enzyme to react. Think of it as a reagent. So you have the enzymes, which brings everything together and reduces the entropy of the entire system. And then you have a coenzyme, which does the work. And so the coenzyme that does the work here is this stuff here, which is a form of vitamin B1. Now, the phosphate we don't need to worry about. We don't need to worry about this. The business end is this part here. So this is the business part of the molecule. And so we're going to abbreviate this whole big molecule, and we're just going to look at this central part. And what the reaction we're looking at is pyruvate to acetaldehyde and CO2. Pyruvic acid is this alpha keto acid, okay? And so pyruvic acid can be converted to acetaldehyde and CO2. this is, by the way, this is not the same decarboxylation that we saw for the beta keto acids. And of course it's not, because that decarboxylation doesn't require complicated machinery. That decarboxylation takes place just very easily with acid. This one is a little bit different. Notice this isn't a beta keto acid, this is an alpha keto acid, alpha carbon, beta carbon, alpha, beta. So this is an alpha keto acid. Okay, so this central business end of the coenzyme has a unique proton, the proton that's flanked by the positively charged nitrogen atom and the sulfur. So there's no other proton in the entire molecule like this. And so this proton has a pK of 18, so it's not particularly acidic. But within the active site of the enzyme, pyruvate decarboxylase, there's a base that can pull that off. And part of what helps that happen is a proximity effect. In other words, the base is held by the enzyme in close proximity to that proton, and so it becomes likelier that that proton, even though it's not very acidic, is lost to that base. What you end up forming out of that is this charged compound. Now, the negative charge here is in an sp2 hybridized orbital, so it's not resonance stabilized with this aromatic ring. However, this electron pair of the negative charge is stabilized by two things. By an inductive effect. In other words, I place the negative charge adjacent to a positive charge, so there's a Coulombic stabilization, but also sulfur has d orbitals that are empty. And those d orbitals can delocalize that negative charge, that electron pair. So that electron pair is moved into, at least in part, the d orbitals that are on sulfur. Now, this species here needs to remind us of something. And what it reminds us of, a little bit, is something we talked about in chapter 18. Remember, we talked about NHCs. What were NHCs? N-heterocyclic carbenes. These were ligands for organometallic species that we saw, I think, in the first time in the context of drugs catalyst 2. And they have either a double bond, sometimes a single bond here, nitrogen, nitrogen. You'll have R groups here, and then you have a plus minus like so. Okay, so an N-heterocyclic carbene is this. This turns out to be an L-type ligand for a lot of metals. That is exactly what you have there, except instead of a nitrogen and a nitrogen, you have a nitrogen and a sulfur. Same thing. So this is a heterocyclic carbene. It's also an ylid, like the Wittig reagent, because you have a plus and a minus charge on adjacent atoms. And it is a nucleophile. So this nucleophile adds to the ketone portion of pyruvate. And it just does the same kind of nucleophilic addition that we've seen before. The pyruvate is activated by acid prior to that. Here's another mistake people made on the exam. When you have a nucleophilic addition that takes place to a carbonyl under acid-catalyzed conditions, which form of the carbonyl electrophile is going to be more active? The one that has the proton attached to the oxygen, like so, or one that doesn't? The one that does, because here I can write a resonance structure that places a full positive charge on that carbon atom. So what a lot of you did was, you did the nucleophilic addition first, generated a negative charge, said, oh yeah, now this reacts with a proton. No, that's doing it backwards. The proton has to be on the carbonyl before the nucleophilic addition takes place. So this proton comes from the enzyme. Okay, so the enzyme does two things. Pulls off a proton here, adds a proton there. Activates this as a nucleophile, activates this as an electrophile. And so nucleophilic addition takes place to form a red bond right there. Now, this species, forget about everything out here. Just look at this part right there. That should remind you of exactly what we saw for the beta ketoester decarboxylation. In fact, it's very closely related. And so I can push arrows, in other words, move electrons, in pretty much the same way I showed just moments ago for the decarboxylation of the beta-keto acid. And when you do that, you can see that you lose CO2 from this piece, and then what you're left with is an enol. That's an enol right there. Now, it's not the same kind of enol that we've seen before. You have sulfur and nitrogen and all of this, but it is an enol. Now, if it's an enol, and it's not just an enol, it's also an enamine. Look at that. This is an enol and an enamine right there. So this is an enamine, that's an enol. Bottom line, this double bond is activated, highly activated. So it's a more nucleophilic double bond than others that we've seen. And so with a proton, you can transfer a proton to this carbon atom, like so. And then you have a tetrahedral intermediate that can collapse, and it gives you right back your ylide and the protonated aldehyde. It's really clever. I mean, you think about that. You have this enzyme that does something really quite remarkable. I have to tell you that this kind of enzymatic catalysis has its counterpart in synthetic organic chemistry too. So there's a lot of ingenuity that's gone into designing organic catalysts that have pretty much this kind of structure that are used for not just decarboxylations, but also for carbon-carbon bond forming reactions, much more interesting. And you can see how that might work, right? Because here, the electrophile is a proton. It didn't have to be. If that electrophile were a carbon atom, then there would be a way to use this machinery to make carbon bonds. And that actually is done. So, this is an interesting mechanism. We've not really seen anything quite like this before. So please, take a look at this, make sure it makes sense, and then try to reproduce it. And make sure that you understand, what happens at this step and at that step. This is kind of the tricky step. The proton transfer at the end is kind of the tricky step here. So that pretty much wraps it up for chapter 20. And I mentioned that chapters 20, 21, 22 are kind of the heart of organic chemistry because it's where we learn about carbonyl chemistry. And so carbonyl chemistry is really where it's at. I mean, that's a lot of biochemistry depends on carbonyl chemistry too. And so what we learn has a direct application in biochemistry. I mean, you just saw that moments ago with this decarboxylation, but there are many, many more examples of that. Now, in chapter 21, we're going to look at not just ketones and aldehydes and carboxylic acids, but we're going to look at carboxylic acid derivatives. Now, what do we mean by a carboxylic acid derivative? What we mean is something that can be derived from a carboxylic acid and, critically, something which can be converted into a carboxylic acid. So all of these species that we're going to learn about, we can either prepare from a carboxylic acid, or we can turn them back into one if that's what we want to do. So let's take a look. Y is something that's not carbon. If Y were a carbon atom, that would be a ketone. If Y were a hydrogen atom, that would be an aldehyde. But if Y is something other than a hydrogen or a carbon, then we have, it's an OR, an alkoxy, it's an ester. A cyclic ester goes by a different name. It's called a lactone. If it's a nitrogen, it's an amide. A cyclic amide goes by a different name. It's called a lactam. That's an A there. So lactones, cyclic esters, lactams, cyclic amides. Acid fluorides we've seen, anhydrides we've seen, nitriles we've seen. And now you look at what these 6 compounds, and they all look pretty much the same, except you look at the 7th nitrile and you say, well, gee, why are we including this in there? Because look, here we have a carbonyl, 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 carbonyl all the way around, sp2, sp2, sp2 all around, sp and nitrogen. This is a different category, isn't it? And the answer is yes, you're right. It is a different category, and it is different from the others. However, the reactivity, as we're going to see, is closely related. And so from a logical point of view, it kind of makes sense to include the discussion of nitriles, the discussion of esters and lactams and lactones and what have you. So we're going to talk about nitrile chemistry in the same discussion, and you'll recognize that it's not exactly the same. It is different, but after you've seen the mechanism, you say, oh yeah, that actually does make sense. Okay, so we need to talk a little bit about the normal stuff, the nomenclature and whatnot. You've noticed I've not asked you questions, and I will not ask you questions about nomenclature on exams. Please take the time to study the nomenclature a little bit, especially those of you who may be taking a GRE chemistry subject or a MCAT, because my suspicion is that you will see on those exams some nomenclature questions. And so, the rules are not all that hard. You can figure them out on your own. You don't need to explain them to you using valuable classroom time. We'll go over this quickly. If it's the ester of acetic acid, so notice if I just look at the left-hand side, that's acetic acid. And the way I name that is ethyl, because this is from ethanol, ethyl acetate. That 8 business here means it's an ester. So if this is butyric acid, 4 carbon atoms, that's a phenyl. This would be phenylbutyrate. So ethyl acetate, phenylbutyrate, not too long. If it's malonic acid, remember oxalic, malonic, succinic, and so on, all my said. So then this would be dimethylmalonate. If I had a methyl and an ethyl, it would be ethyl methylmalonate. And now if it's a lactone, these are named a little differently. This would be named, first of all, it's got 4 carbon atoms, 1, 2, 3, 4, so it's butyr, right? Butyr is the suffix, the prefix, pardon me, for 4. So this would be butyrolactone. But of course, there's more than one butyrolactone. And so, when I say butyrolactone, I could be talking about the compound I just showed you, or I could be talking about that compound too. That's butyrolactone. And it's butyrolactone because I have 1, 2, 3, 4 carbon atoms since the lactone. But this one would be a beta butyrolactone because the carbon bonded to the oxygen is beta. On the other hand, this is gamma butyrolactone because the carbon bonded to the oxygen is the gamma carbon atom. So beta butyrolactone and gamma butyrolactone. Acetyl chloride, acetyl bromide, I don't think I need to explain that. And then for the cyclic ones, we kind of went over the cyclohexane carbonyl chloride. So this whole unit here, COCl, carbonyl chloride. So for cyclic compounds, it again is a little bit different. You can name it sort of as a substituent, if you will, of the ring. Remember, we had cyclohexane carboxaldehyde. So carboxaldehyde, if I had a C double bond OH, if I have a C double bond O chlorine, then it's not carboxaldehyde, but carbonyl chloride. Anhydrides, I mentioned this last time, that anhydrides don't have to be symmetrical. So in other words, here's an unsymmetrical anhydride. So it's an anhydride that you get from formic acid and acetic acid, so 2 of them. This is actually a useful reagent, I'll explain in a minute. This is alkylized, so acetic formic anhydride. Okay? Now, why is this useful? Well, it's useful because you say, well, why do we need that? Well, okay, so I'll leave this up here. You can imagine that formic anhydride would be a useful reagent. Now, the trouble is you can't make this. This is not stable. Just the way this isn't stable, this isn't stable. This stuff, if you try to make it, it decomposes into what? Into water, CO2. Or, I can't remember exactly what you get out of this, but it seems to me you get carbon monoxide out of this too. I think, yeah, what happens to the outside? So what this thing decomposes to is formic acid and CO. And so, so you can't make this, but you can make the mixed anhydride. Of these 2 carbonyl groups, the one on the left and the one on the right, which one is the more reactive? So which you know, if I have a nucleophile, and a nucleophile wants to react with this, is it going to want to react here or there? Why? Right here, that's correct. And the reason is because this carbonyl group, like an aldehyde, is more reactive than this one. Why? Well, because the hydrogen is less electron donating than the methyl. Therefore, delta plus is greater there and smaller there. And so that's how you get around the instability of formic anhydride. You can't make formic anhydride, but you can make formic or acidic formic anhydride, and that reacts just the way formic anhydride would. Transfers the formyl group. Okay, so cyclic anhydrides, this is, oh my, such good. So butyric anhydride. For nitriles, you look at if you have two carbons, it would have been acetic acid, so that's acetonitrile. If you had a phenyl ring, it would have been benzoic acid, so it's benzonitrile. If it was a cyclohexane carboxylic acid, it's cyclohexane carbonitrile. So carbonyl chloride, carboxaldehyde, carbonitrile. Okay, so cyclohexane carbonitrile. Amides, these here you need to, when they're alkylated, you need to specify that the alkyl group is on nitrogen. Okay, so if it's acetic acid amide, then acetamide. That's a primary amide. This is a tertiary amide because I have both these hydrogens substituted. And you have to specify NN. The NN means dimethyl acetamide. It tells you that the methyls, both of them, are on nitrogen. Okay? So if I had N-methyl acetamide, that would mean I have one methyl on the nitrogen, a hydrogen, and so on. So this would be N-ethyl cyclohexane carboxamide. Secondary amide is only one alkyl, and the N-ethyl tells me that the ethyl group is bonded to the nitrogen. So you know, once you see the name, it's self-explanatory. Going, as I said, from the name to the structure, easy. Structure to name, a little bit harder. So I would expect you, given a name, to be able to figure out what we're talking about, in other words, the structure. Now, for cyclic amides are lactams, right? And beta propiolactam. Why propyl? Well, just 1, 2, 3, propionic acid. And beta because beta carbon has the nitrogen. Why is this important? Why is this substrate? I mean, this looks like a weird thing, right? I mean, gosh, 4-membered ring lactam, you know, who cares? Why is that structure really, really important? It's part of penicillin. It's actually the reactive part of penicillin, and it's the reaction of the beta lactam that kills off bacteria. Okay, so this is a substructure of a very important class of antibiotics. So as you can imagine, a lot of human ingenuity has gone into designing synthetic chemistry around this structure because of synthetic antibiotics. Okay, so a lactam is a cyclic amide. An imide is the nitrogen equivalent of an anhydride, okay, a cyclic anhydride. So if I have and it does have a cyclic, by the way, I just showed the cyclic one. So an imide is a compound that has nitrogen with two carbonyls attached. So this is N-bromosuccinimide. Remember, this was the reagent used for free radical brominations. So, and the N tells me that the bromine is bonded to the nitrogen. The N-phenyl tells me that the phenyl is bonded to the nitrogen. Why glutaramine? Well, because, oh my, such good, glutaric acid determinant. Now that we know these functional groups, we have a expanded list of principal groups. You don't have to copy this. It's in the appendix of your book. So what's a principal group? Well, if you have one or more of those, then the one that's highest priority on that list dominates the nomenclature. So in other words, if I have an alcohol and an acid, I don't name the compound as an alcohol, I name it as a hydroxy acid. And acids have higher priority than anhydrides and so on and so forth. There's absolutely no logic to this. It's just a rule that was made, and it was made at a time, I told you, when finding information in the literature depended on an alphabetical search of a printed index before computers. And so you needed to know the name or you couldn't find stuff. So it was important at one point. Nowadays, thank God, the searching of literature can be done using a graphical user interface that works pretty well, where you can draw a structure and look for stuff. And so knowing the exact proper name is not anywhere near as important as it used to be. But at one point, this was a really important skill to have. And so that's why so much effort has gone into nomenclature, making it systematic and unambiguous, okay? Now, there are also some names we need to know for substituent groups. And in other words, if I have a molecule that has a COOH attached to it, then that's a carboxy, or a cyan, or carbamoyl, this one always confused me, acetoxy, and so on. These are names that you probably do want to try to remember. Certainly carboxy, acetoxy, cyano, and whatnot. How many chloroformyl groups you'll see, or ethoxycarbonyl groups you'll see in this class, I don't know. But I'll try not to tax your memory by expecting you to remember that stuff, but you should make any effort to do so. One reason for you to do that is because it makes your reading faster and easier. Okay? So if you know what they're talking about, you don't have to go look it up every time. So carboxy, cyano, and so on. Now, moving along, we always look at after we cover names, we always look at the physical properties and structure and whatnot. And unsurprisingly, carbon-nitrogen triple bonds are shorter than carbon-carbon triple bonds, just a difference in electronegativity, and significantly different, shorter. It turns out something, and this has real, so this is an interesting observation. This is much more important. It turns out that amides have a shorter CN bond than you would expect, and also that these two R groups don't exchange very fast. So, don't exchange, that's a bad way to put it. These two R groups are distinguishable by proton NMR, and by C13, that's what I mean. So, in other words, if I have rotation around this CN bond, fast rotation, then the R1 and the R2 would be in identical environments, but because they're not, if I have a compound like dimethylacetamide, or dimethylformamide, that makes it that. If you look at this compound, which is dimethylformamide, you would expect to see a single methyl peak because these are equivalent, and a singlet for the aldehyde type proton. But in fact, these two methyl groups appear as two different singlets. And the reason for that is because of the resonance structure that places a negative charge on oxygen, a positive charge on nitrogen, and which looks now like a double bond. So I have an E and a Z, if you will, methyl group. So these two methyl groups are not in the same environment. Now, it turns out you do get rotation around here, but that rotation is really, really slow compared to a normal CN bond. How slow? I can't remember, but it's about between 5 and 10 rotations per second, which sounds fast, but not compared to this kind of unhindered rotations that we've seen for other kinds of bonds. And in any case, even at 10 rotations per second, that's very, very slow compared to for an NMR experiment. And so as a result, these two methyl groups appear as a singlet and a different singlet. And the first time you see that, you don't know what's going on. Then you think about it, think, oh yeah, that's resonance structures come to life. That really makes it real. When you see that NMR effect, then you realize, boy, this resonance thing really has some validity. So the activation barrier here is pretty high, 17 kcals per mole. And so it's almost like you have, well, you have a partial double bond there. So that turns out to have some implications in structural chemistry as well. Esters, I think I mentioned to you that whereas carboxylic, low molecular weight carboxylic acids typically have kind of nasty smells and biting smells. They just kind of, you get a whiff of that, you just recoil, actually. Esters, on the other hand, have really nice smells, many of them. And so a lot of fruits and foods have the flavor and the odor is largely caused by esters, also aldehydes, but esters too. And so if you were to smell this compound, you would immediately recognize banana. But at the same time, you say, well, it smells like banana, but banana is more complicated. And that's because bananas have, the smell and odor of banana is dependent not on one compound, but on a mix. And so, anyway, we used to make, let's see, we used to have students make this compound in the lab. I don't know if you guys still do that. So esters are volatile, and one of the reasons that they do function as odorants is because they get into the air, right? In other words, if those esters were really, really high boiling, then there'd be a tiny concentration in the air. Maybe your nose couldn't pick it up, but because they have fairly low boiling points, they have these nice odors. And so if you compare something like propanoic acid and methyl acetate, which have the same number of carbon atoms and oxygens, you notice there's a pretty huge difference in boiling point. That's because this hydrogen bonds that doesn't. I mean, you know that. So anhydrides and acid chlorides also don't hydrogen bond, and I already told you that. But anhydrides and acid chlorides have really awful smells. So those little, they choke you. They're so bad. And nitriles are extremely polar. And so nitriles have very high boiling points, and even though they can't hydrogen bond, because they have this strong dipole moment associated, they have high boiling points. Typically, they don't have very characteristic odors. I mean, they have a smell, but I can't, there's no kind of odor where you say, oh yeah, that's a nitrile. That you don't have. So notice the difference between acetonitrile and just propyne. Boiling point here is about 100 degrees apart. The reason is that this thing has that huge dipole moment holding molecules together. Amides, as you can imagine from that resonance structure that I showed, from this resonance structure, you can imagine that amides also are polar molecules, and because they have a molecular dipole moment associated with them, amides also should be high boiling, and they are. And so if you look at acetamide, for example, very high boiling. Of course, as I take these hydrogens and I put methyls, look at what happens to the melting point and the boiling point. Both of them go down, and the reason is pretty obvious because all three of these have a molecular dipole. As the number of hydrogen bonds that they can form diminishes, then the melting point and the boiling point goes up. So in other words, here I have hydrogen bonding, here I have a little less hydrogen bonding, here I have no hydrogen bonding, and that's reflected in boiling point and melting point. So what we talked about way back when we talked about properties and hydrogen bonding and all that, here it is again. I mean, nothing surprising, right? I mean, this is all stuff you've heard before. And I don't expect you, for God's sakes, I don't expect you to remember boiling points or anything, but I do expect you, confronted with a difference in boiling points or melting points, to be able to figure out that, oh yeah, that's because this one hydrogen bonds and that one doesn't. That's the importance of this. The numbers are not what's important. The concept is important. Okay. So this hydrogen bonding, as you can see here, really overwhelms the increased molecular weight. Of course, this has higher molecular weight than that. This has higher molecular weight than that. But the hydrogen bonding interaction is what really dominates that. DMF, dimethylformamide, that turns out to be a very common solvent. And it has notice that the epsilon value is huge. What does that epsilon value mean? That, remember, is the measure of how well a compound can stabilize separated charges. So I take a plus charge and I start pulling it apart from a negative charge, that costs me energy. If the epsilon value of the solvent is high, it costs me less energy. And so, in other words, if I want to do a reaction that requires soluble ions, then DMF would be a good solvent to do it in because it's not going to cost me very much energy to take that ionic solvent and pull those ions apart and dissolve them. So this is going to be a good solvent for ionic compounds. Yeah. And it's, as I said, common industrial and laboratory solvent. Okay, so now that we know something about spectroscopy, you kind of know how you would distinguish between these carbonyl compounds, right? I mean, look, we've got, these are the compounds we talked about, and now let's look at the nitrox. Okay, so let's look at all of these, and you have the carbonyls, nitrox. So if I wanted, if I had a compound, I knew it was one of these 7, I could immediately tell whether it's a nitrile, right? Because the nitriles are going to absorb in the triple bond part of the infrared spectrum. So infrared will be a really good tool for figuring out if I have a nitrile. All I have to do is look at the 2100, 2200 region. If there's a strong peak there, then I can be absolutely sure it's a nitrile. And if I don't have that, and I've got something in the carbonyl region, then it's one of these. But which one? Well, okay, so now we need to think a little bit about that. If I have an electron withdrawing group attached to the carbonyl, when you guys walk in late, can you please not slam the door? Thank you. If I have an electron withdrawing chloride attached to the carbonyl, then it's costing more energy to stretch that bond. And so the IR frequency for this kind of a carbonyl is going to be higher than, say, for a ketone. And so it turns out that IR will distinguish between all of these and will do a pretty good job. Now you can say, well, how good a job? Well, okay, so some overlap. Okay, so it's not perfect, but it's pretty good. Esters are at a higher frequency than ketones and aldehydes. Okay, so remember, ketones are on 1700, aldehydes on 1720 or something. Now, if I go higher than that, almost 1750, that's clearly not a ketone or an ester. Acid chlorides, remember what I said about electron withdrawing groups? This takes you all the way out to 1800. So you look at 1800 and say, well, that's not, I thought carbonyls were 1700. What's this thing doing at 1800? Well, it is a carbonyl, but it's a carbonyl group that has a strong electron withdrawing group attached to it, right? And so if that happens, then yes, the frequency for that carbonyl will go way, way up. Anhydride's not quite as high, and typically 2 peaks for anhydrides. Why 2 peaks? Well, okay, so because you can have the anhydrides stretching at the same time, or one stretching and one contracting, and so you get different peaks for those 2 vibrational modes. Amides, on the other hand, are at a lower frequency than ketones, And you get, if it's a primary or a secondary amide, then you also have some NH peaks to look for. And then nitriles, as I said, on 2200, so that's kind of nice. You can tell the difference between all of these pretty much. Now, is there overlap? Yes, there is, and so when you have an anhydride or an ester, look, there's a little bit of overlap there, and so you can get goofed up. But in general, you have other data in addition to the IR that will distinguish between them. The IR is, by the way, the IR is used for functional group distinguishing. Okay, so that's why we talk about it here. Okay, so I'll have your exams on Wednesday when I meet again.